Now we are going to talk about sets. Now, before I cover the content that I want to cover about sets, we'll briefly go over the types of sets that I'm going to mention here. So you have discrete sets. So S1, for example, can be equal to 1, 2, 3. There's a finite number of values, and this is a discrete set. And likewise, S2, if it's equal to 1, 3, 5, 100, 201, this is also a discrete set. There's a finite number of values. There are also sets that can contain an infinite number of values. So S3 is equal to, for example, it contains all the positive integers. Well, that would be 1, 2, 3, 4, 5, and so on. There's an infinite number of positive integers. Now, there is an infinite, but this is countable because you can actually count it 1, 2, 3, 4, 5, and so on, all the way to infinity. It's countable. You know exactly what number comes next after 5. That's 6, right? And 7, 8. However, there are also compact sets, which contain an uncountable infinite number of values inside. So set 4 is equal to, say, all the irrational numbers. Well, then, for example, 0.1, 4, 2, 8, 9, 3, and then goes on, and then 0.1, 5, 7, 8, 3, 0, 2, and goes on, and 1.2, how about 3, 1, 4, how about this, 7, 0, 2, 8, and just goes on, right? So there is an infinite number of irrational numbers. However, it's not countable. Like, just take this number here, 0.142893, and goes on. Can you find the number that's like directly after? Like, okay, what's the number directly after? Well, well, you can't do it like you did with the number of positive integers, right? So uh, this is an this is an uncountable infinity number of items in this case, and this is a compact set. Now we're going to go over set operations. Set operations. So what are set operations? Well, I'm going to give a few examples for you so that you can understand them. So first, let's start off by knowing that you can actually visualize sets with a Venn diagram. So here is a Venn diagram, and oh, this part has set A, right? And this part has set B. Now, here, what is this part? Well, this is the intersection between A and B. And here's the first set operation I'm going to present to you. So here, this part can be written as A intersect B. Looks like an N, right? A intersect B. And let's say that the set A, sorry, contains, for example, 1, 2, 5, and 3, right? And let's say that set B, it contains 1, we can, how about this? 3, 7, and 2, right? 3, 7, 2. So what is A intersect B in this case? Well, it's all the values that belong in both A and B, since that's the properties of the values in the intersection. So A intersect B would be 2 and 3. Now, if I were to remove 3 from set A and just leave it like that, then what's the intersection? Well, the intersection is a set containing just 2. And notice it's not just the number 2 itself, right? I didn't just write the number 2, right? You should write a set that contains 2. Now, I'm going to go back to including 3 in both sets, so then the intersection will be 2 and 3, a set that contains 2 and 3. And there you go. Now, the next set operation I'm going to be talking about is union. So this time we're talking about union, and union covers the entire area. Union covers the entire area. And please note that we only count the intersection once, right? The intersection is only counted once, and we're not supposed to double count it. So to write this, it's equal to A, and then union looks like a U, and B, A union B. And please note that this is not equal to, in this case, this is not equal to A plus B, like this. Because what happens if you actually do write A plus B? Well, notice that if you do A plus B, just A plus B, well then you're adding this entire area, right? You're adding this entire area. So that's A. So that's A. But then you're going to add a B. So you're adding this entire area. But notice that you're counting the intersection 2 times. So in this case, the A union B is not actually equal to A plus B. It's actually equal to, so now it's going to be equal to, it's going to be equal to minus the A union, sorry, A intersect B, since you double counted the intersection. And in this case, with our examples here, with this example above, A union B would be equal to, you would see that you would write 1, 2, 3, 5, and 7. Now notice we didn't write 1, 2, 2, 3, 3, 5, 7. Why? It's because we only count the intersection once. Now, if we did A, for instance, A plus B, what would this give us? Well, then in this case, remember when we didn't subtract the intersection, we did double count the intersection, right? So in this case, you would get 1, 2, 2, 3, 3, and then 5, 7. So in this case, A plus B and A union B, different. So in this case, right? Now we're going to go over the next set operation, which is the difference of sets. Difference of sets. So what is the difference of set? Well, you write it as A. Maybe we can write this a little bit bigger. So A, and then slash to slash, and then B. And essentially what you will get, the result is all the values that are in A and only A. So it doesn't include the intersection because the intersection here also, the values are also included in B. So the result is actually only equal to the values in this area, not including the intersection. Not including the intersection. So in this case, what would the difference in this case be equal to? Well, here the only values that only belong to A are here, 1 and 5, right? 2 and 3 are in B, so it would be 1 and 5, a set that contains 1 and 5. Now, what about the next operation, which is the complement of a certain set? So the complement of a certain set would be, for example, I'm going to use a different diagram this time. The complement of a certain set would be the values that are not in that set. So here, this is the entire space, right? And here is set A. Sorry. So this is set A. Now, the complement of A would get you the values outside of A, right? The complement. And to write this, you can suppose that the entire area here, everything here is S, right? And you want to do the difference, and that's A. And in this case, you're going to get the complement of A, everything outside of A. I want you to think about why the following are true. A intersect B, and the complement of it, so if I write a bar on top, that's actually the complement. So not A intersect B, think about what that means. Complement of A union the complement of B. Why is this? And also, the complement of A union B, this is equal to the complement of A intersect the complement of B. Why is this once again? Now you can use a diagram. You can use this a diagram, a Venn diagram, to actually to help you visualize it. For instance, the not A intersect B is anything outside of A intersect B, right? And A union B, if you just draw a space outside, well, that would be the entire area outside of the entire Venn diagram, right? So use this diagram to help you to visualize why these two statements are true.